Hi, in this video we'll talk about the cosine signal plus noise model and how to forecast from that type of a model. Recall that our last video was about the line plus noise model, and in general this chapter 8 is about the signal plus noise model. Now the signal can be a number of different signals, and the two that we talk about in this chapter are the ones I just mentioned. The line could be the signal, plus a cosine curve could be the signal. So those are the two different types. And this particular video is about the cosine signal. So let's go over to R, and we will, let me get rid of that plot, so we start fresh here. All right, let's generate, first of all, a cosine plus noise model. Our purpose for doing so, it's going to be one where, of course, we generate one where we know the answer to. We know the parameters. Then we'll try to recover those parameters with our methodology. And if we do that successfully, then that is evidence that our methodology is solid and that we could be able to do that on a data set that we don't know the answer to. So first of all, what we're going to do is we're going to generate an AR1 that has phi1 of 0.75 and a variance of the A terms of 1.5. Let's run that. There's the plot. We're going to let time go from 1 to 100, which matches the length of the realization up in the line before it. Then we're going to create this cosine curve. We'll call it sig.cos for signal. 5 times, so the amplitude's 5 times cosine 2 pi times 0.1 times t plus pi over 3. So the 0.1 is the frequency, that's the F, and the pi over 3 is the phase shift. So let's do that, and then we will plot it, and it looks like this, as we would expect. And then we're going to sum those two up. By those two, I mean the Z, that's the AR1, plus the cosine. And that's how it gets its name, the cosine plus noise. So the noise is referring to that AR1. So let's sum those up and then plot it. And what do we expect? Well, we expect it to be a sum of those two plots we'd seen before. And there it is. Now, here's the way that we're going to go about this. It will look exactly like it did for the line plus noise. In other words, remember for the line plus noise, what we had to do was once we did determine it was a line, and by the way, we're going to have that issue here for the cosine signal, we have to truly ask ourselves, do we seriously believe that this is a cosine curve and that it's going to continue in the future? That's a tough call. But we'll get there, and we'll talk about that at the very end of the video. But let's just assume that, yes, we do believe that it is a cosine curve. And as I said, just like we did in the line, when we know something's a line, what did we do? Well, we estimated the B0 and B1 of that line, and then we fit an AR to the residuals. That's exactly what we're going to do here. Now, it's not B0 and B1. For a cosine curve, it's going to look more like, if you go to section 8.21 and go to formula 8.10, you'll see that we write that cosine signal plus noise formula in a different way than how we started. It's going to look like x of t equals c naught, that's the constant term, that's the c naught we're talking about here, plus a, that's amplitude of the cosine term, a times cosine of 2 pi ft, that's this a, plus b, that's the amplitude of the sine term, b times sine, I know this is a cosine curve, but we're still writing it as sum of sine and cosine, b times sine 2 pi ft plus zt. And the zt is that zt term that we saw in the line plus noise that we're going to model by an AR. So obviously we've got to estimate C naught, A, and B, and the way that we do that is the process here. We let n be the length of whatever x dot cos is, which is what we defined up here, right? It's really the length of the realization. So we'll run that. We then have a filler for this, what we're going to call H1 and H2. We're going to fill it full of zeros. And then we're going to say that our f dot estimate is 0.1. It's sort of more than an estimate. We know it's 0.1 because we can see it up in the model, right? But if we have a actual data set that's a real data set, we don't know f. How would we get that frequency? A couple of ways. You could look at the spectral density, and that could let you know. It also may be pretty visible by the eye. If it's truly a cosine curve, it's not that hard to find the frequency because you know how long it takes for this data set to cycle through. So how long is a period is what that would let you know how to get to the frequency. So we're going to let that be 0.1, and then we define this cosine times 2 pi times f dot s times t. That's just the cosine part. And do the same thing for the sine. So we have two big matrices of 100 values each. And then look what we do. Here comes this estimation piece, LM for just the regular linear model, x dot cos, because we can really, when we wrote it in that form of 8.10, it's now linear. And because of that, we can use this linear model form to estimate our parameters. So x dot cosine tilde h1 plus h2. So we are trying to get the coefficients for h1 and h2, and also the constant term as well. And here they come. We can see that the intercept, the C naught is negative 0.03. The H1, which is really A, 2.759. And H2, which is really B, is negative 4.664. We're going to see that more clear here. Here's the residual. We're going to set up the residual because we're going to fit an AR to the residuals. And we filled it with zeros. And here's our C0. So it's H dot S, coefficient 1, that's C0. Coefficient 2 is our A. And coefficient 3 is our B. Which gives us the values that we had seen before. So we really had some repetition there. We'd already seen that up here. Negative 0.0339, 2.79, negative 4.6, negative 4.664. Okay, so we now have our estimates of C naught, A, and B. And now we put all this together to get our residuals. So for t in 1 to n, z dot cosine t equals x cosine t minus c naught. So we're calculating the residuals. We're subtracting it out, one side minus the other, minus a times h1t minus b times h2t. So just algebra here. And we call that our error terms, z dot cosine. There they are. Now, as I said, just as we did in the linear, in the line plus noise setting, we're going to fit an AR to those residuals. Run that. That estimates and returns the parameters of the AR1, and it calculates the residuals. So now what we're doing is we're going to estimate this. We're going to give it the z dot cos from what we had just defined. And then we know that the order P, we're fitting an AR to it. Whatever that order was that was found here needs to be inserted here. That's what we're doing next. There's our AR1. And here are the residuals. And then what do? We could get just like we did in the line plus noise, we can get the forecast of the residuals. That's what's going on in this step. Probably should have been labeled there, forecasting of the residuals. How do I know that? Because I can see this argument right here, AR.cosine dollar sign residuals. So we're getting the forecast of the residuals. How? Well, by the phi coefficient that we found before. There's only one of them because it was an AR1 that was fit to those residual terms. And then we chose to have 50 forecasts ahead. So again, this is the forecast of the residuals. Let's run that and see what we get. Okay, what do we see here? Well, this was the actual data out to 100 points. Then here comes in the next 50 different forecasts. What do you see here? Well, what we see is, just like we did in the line plus noise setting, the residuals we know